Welcome, Mechanics of Materials students. This is the second recorded lecture for our section on strain energy. If you are following along in the notes, you'll notice that we are on notes page 5. There is an example preceding this one that makes use of the concepts that we've covered in the strain energy general expression derivation, but we're going to take a pause and hold that example until we get to our section on general uniaxial stress applications, because that example makes use of a strategy for using Hooke's law to evaluate statically indeterminate systems. And then once that's been done, you end up having stress and strain and then can apply strain energy. We're going to start with an example that is more simple and where the application of strain energy is a little bit clearer, and then we'll loop around and come back to that other example when we get to our chapter on uniaxial loading applications. Okay. So for our example here, we have a rectangular body, and it's uniform material. It's aluminum, and we've been given some elastic constants. We've got our Young's modulus or tensile modulus 70 gigapascals. It's got a Poisson's ratio of 1/3, give or take, 0.33, and we're going to be looking at some temperature changes. So we've got our alpha, our coefficient of thermal expansion, of 23 times 10 to the minus 6 per degree K. So we'll end up getting a strain once we multiply that by whatever our temperature change is. So here's our body, and it's subjected to some distributed loads. So we've got 200 kilonewtons per meter being applied along this face, which is kind of basically like our X face. We have on our Y face, Y positive and negative Y face, we have 1,000 kilonewtons per meter being applied. So in order to get the uniform stress on those faces, we'd have to include our other dimension, which is our 20 millimeters of thickness. So we have 200 kilonewtons per meter acting in compression, acting on our positive and negative X faces. If we want to get the stress or pressure, so to speak, on that X face and negative X face, we would divide again by this dimension. And likewise in the Y. So we have stresses only, normal stresses. We have no applied shear stresses. And we're in a state of biaxial stress, so plane stress. There's nothing going on in the Z direction. You can see this is our Y direction and our X direction. We're also told that we have 100 degree K temperature change. So we're asked 3 questions. What are the strains? What are the body dimensional changes? How big, small is it going to get? So think displacement. And neglecting the temperature change, what is the elastic strain energy? So the big thing about neglecting temperature is, remember, our strains have that temperature component. So if we're looking at the elastic strain energy without that temperature component, we're going to take only a portion of the expression for strain when we tally up our strain energy. Well, without any applied shear stresses, it's a good thing we didn't have since we didn't have a shear modulus, but we're basically using just the axial or normal stress component of Hooke's law. So first we start, like I said, by going from just a distributed load to a stress. So for our X direction normal stress, we're going to start with our 200 kilonewtons per meter compression. So notice we've got our negative sign there. We're going to divide by the thickness, and so we end up with negative 10 megapascals. So that's negative 10 times 10 to the 6 newtons per square meter. We do the same thing in the Y, and we get 50. So now I have a sigma XX and a sigma YY, and we drop down. We can apply Hooke's law. and get our corresponding strains in the x, y, and z direction. So we of course have our 1 over our elastic modulus times the stress in the normal stress in the direction of strain we're looking for, minus Poisson's ratio times the sum of the two normal stresses in the orthogonal direction. Of course, since we don't have anything in the z, we'll just basically have the opposite normal stress populating our Poisson's area. So in the z direction, we don't have any normal stresses in the z, but we have the sum of the x and the y normal stresses. So we are definitely going to have strain in the z direction, even though we don't have any applied stress because of Poisson's effect. Now, something we don't see all the time is that last component of our stress, or excuse me, our strain expression, which is our linear coefficient of expansion. So we're going to get strain in the x direction due to stresses in the x, Poisson's ratio times stresses in the y and z, and then thermal expansion or contraction. So in this case, we have 100 K increase in temperature, so our delta T is positive, so this value will be positive. And again, we get that, we're given alpha, so we'll have 23 times 10 to the minus 6 per degree Kelvin times 100 degrees Kelvin will be this term. So if we pop in all of our values, our elastic constants and our given values, we get 1.92 times 10 to the minus third, 3 times 0.0 times 10 to the minus 3, and 2.11 times 10 to the minus 3. So we're in millistrain, not microstrain. So this thing's really changed size and shape quite a bit. Other things to note, in spite of the fact that we have compressional stress in one direction, we have a net strain that's positive. Everything got bigger. So we probably had some shape change, but we also had a net dilation. So and that was very likely due to this thermal expansion component, which was positive across the board. Okay, so next, so we've completed that portion. What are the body's dimensional changes? All right, this is easy because our strain was uniform. So we can use our expression for average strain. So we can use our change in length divided by original length equals strain in a normal direction. So we can just apply that to the x, the y, and the z. So we can say our change in the x dimension is our normal strain in the x direction times the original length in the x direction, which in this case was 400 millimeters. We'll do the same thing for the y, 200 millimeters times EYY and 20 millimeters times EZZ, and that'll give us our new dimensions. So we will have grown a little over 3/4 of a millimeter in the x, a little over a 1/2 millimeter in the y, and 0.042 millimeters in the z. So not insubstantial. Okay, last but not least, strain energy. So we're going to break out our fundamental expression for strain energy, 1/2 times the integral over all V of our products of stress and strain. And in this case, since nothing changes with volume, we can pull the volume out of the integral and just express it as a constant. So we end up just getting 1/2 times our product of stress and strain in the x, and then product of stress and strain in the y, and here's our delta V. Again, because nothing in the integral changed with volume, with any position anywhere within the volume, we could just pull it out. So here's our 400 millimeters, our 200 millimeters, and our 20 millimeters expressed in meters. Do not forget to change your units because, of course, pascals are newtons per square meter. So we need to keep units fairly constant. I haven't broken out the megapascals, but this would equate to, in this case, -10 times 10 to the 6th newtons per square meter, We have newtons per square meter times something dimensionless, eventually times meters cubed, which will give us Newton meters, which is joules. And if we tally all that up, we get 33.5 joules. Important thing to remember, this strain, this EXX, is negative, and this EYY is not the same. It's positive but substantially smaller than what we had up here. So the difference in those two values represents discounting, not including our thermal expansion in that expression, because we were asked for the strain energy independent of thermal expansion. So that brings us to another topic that we're not going to get into in any kind of depth. In general, strain energy is it's defined without the contribution of thermal expansion. Why? Because in some cases things may expand freely. So if you have, say, a block of metal and you put it in the sun, it will grow. It will undergo probably a volumetric expansion in the sun. According to that alpha delta T in each of the three orthogonal directions. But because it expanded freely, there was nothing resisting the expansion. There was no force. Even though we had displacement, we had a dr, we didn't have an F to go with it. So there was no work done. There was no accumulation of strain energy. We can envision a case where maybe we restrain something, put something in a vise and heat it up, and we don't let it move. In that case, theoretically, we could accumulate some strain energy. But in that case, what we would tend to do is we would do this maybe by a superposition type principle, where we would determine the free volumetric expansion that the body would have undergone, and then apply an equivalent compressive stress to get it back to that same volume that we made it stay at. So rather than including thermal expansion explicitly in the strain energy equation, we would use a kind of a fake, call it, or an equivalent compressive stress to ensure that in spite of the temperature change, the material stayed where it was. So we would basically apply a compressive stress strain, starting with we would allow the part to freely expand to the new volume, and then we would use stress and strain to put it back to the original volume. And that's employing something called superposition, which we'll get into later on in the course. But in both cases, either a free expansion where you didn't do any work and you didn't accumulate any strain energy, or if you have a constraint in spite of a constrained situation where you have maybe an increase or decrease in temperature, you would represent the strain energy based on an equivalent stress and strain rather than directly including our alpha delta T. So that's one of the reasons why the directions to this example said don't include the impact of delta T in this case for strain energy. So there won't be too many times where you have to do that, but there are a few significant cases where we do have constrained materials that want to expand or contract, and we'll look in future chapters at ways to deal with those, including how to tally up strain energy. So that is it for this example. Like I said, if you're studying along, remember if you are in the strain energy section, just skip to page 5, example number 2. You will see the example number 1 again in the future. It's a little bit longer, and it's actually a flashback to an example that was started earlier in our chapters dealing with statically indeterminate systems and applying Hooke's law to solve them. So that will be coming up in a future chapter.